Ladies and gentlemen, today we are going to take a peek back for a little ways. We're going to do a study guide that can kind of help us get ready for finals. It's a good look at some things, but it also is getting us ready for a post-test. If you remember, back at the beginning of the semester, we took a pre-test to which most of us didn't do very well. We hadn't seen a lot of the topics. Well, now, sometime in May, we'll be doing a post-test to kind of see where you've grown in some of those areas and where some things have improved. And like I said, to get you some extra points in some places based on that growth. So let's take a look here. We're going to do some kind of examples, get you back into the swing of things, give you some references where you might find some things in the notes or some old videos, and then have you try some on your own. So, on this first one, we're going to identify the domain and range of this exponential function. Now, if you don't remember the general rules right away about which one's negative infinity to infinity, which one has to do with the shifts, there's a backup plan, like there is usually anyway. So if I go to my calculator, I bring up the y equals, I can go ahead and I can graph this. Now here's the key on this one. Let me make sure I get my colored marker out to put this in. When I go to put my exponent on there, I have to, not an option. See, you can't do that. It's about to do something silly. You cannot forget the parentheses, because if you do, you will not get the right graph. So speaking of, once I get that typed in, okay, get my graph. Now again, the domain and range of the function, again, domain is my x values from left to right. My range is my y values from the bottom to the top. So when I'm trying to figure this out, I go, okay, so domain, this is going to keep going up and outwards forever to the left, and this is going to keep going forever to the right. So I could write it from negative infinity to infinity. Okay? Covers everything. Now, my range is a little bit different. I notice that it's going to go up, 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 up forever. So I see the infinity part. But does it go down forever? Well, no. It comes down and it kind of cuts off right in here. Now, if I really take a look at the dots, I probably can just count, but 1, 2, 3, 4, 5. But really, what I need to know is right here. Okay, that down 5 means that's where my range is going to start. Okay, if it was plus, it'd be like plus 3. It'd start at 3. And there's that connection. But again, take a look at the calculator to figure out some of that. If you forget the general rule that on those types of functions, domain's just positive infinity, negative infinity, and the range is just the shift, you can always look. Okay, end behavior. Now again, end behavior. You remember when we had the blank, and then we had the x, and then we had the blank, and we had two of these because there's two different things that we're looking at. But the one thing that was always nice was we always knew that the x was going to be positive and negative infinity for us to be able to cover everything. So I get into my y equals. Go ahead. Again, like we did before, if we have a binomial in the exponent, we got to make sure that gets into parentheses. And I graph it. Now this time, I'm looking to see, okay, now how's this work again? As x goes left, what happens to y is what this is basically saying. As x goes left, okay, so as x goes left, what value am I approaching? Well, it looks like it's leveling off right here at 1, and it's not going any lower. Okay. So y approaches 1 as x goes left. That's true. Then, as x goes to the right, what happens? Y goes up, 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 up. Positive infinity. Okay, I'm just going to follow those things when I'm doing these. And that's basically all that I'm looking at for that one. Now again, and I'll mention there will be some help with the formulas. I'm going to help you with some formulas here on too. But we do have to make an adjustment to this one because I didn't quite word this one real well. So let me get this out of the way. Let's move this up a little bit. All right, you deposit $200 in a savings account. Okay, that part's fine. For each year thereafter, I got to read, you plan to earn 15% interest, period. About how much money will you have earned in all after 20 years? Because the type of question we got in here isn't one we really hit on. It was kind of a little bit off. So for this part, okay, it looks like this. So as we continue with this, just a reminder on what some of the values are. A is the amount I start with, so 200. 1 plus my rate. Now again, my rate, I can't just use 15. I have to use the decimal form of this. Decimal form of this would be 0.15. You can either divide that by 100 or you just move the decimal point 2 places to the left. And then since we know the time, we'll go ahead and we'll put that in. And basically, we're going to let the calculator do it, take it from here. Now, some of you will say, can you put it in the y equals? I can. I'll get the same value all the way down. But otherwise, I can just type this part in since I have the value for my variable term. And I find out I will have D331. And again, if you typed this into the y equals that way, you'll get the exact same answer. It's just you're going to see the same answer a whole bunch of times in a row. So again, not too bad there. As we kind of continue a bit. Okay, price of an antique table increases 3.1% annually. If the table is worth $590 in 1980 and this growth continues, create a function that models the exponential growth of the table's value starting in 1980. So, almost the same as the last formula, except for one small difference. And we'll just get rid of that minus because we're not going to have one of those. So again, a lot of the values here are going to be the same. A is still going to be what I start with. My rate, again, be careful. And if you're not sure, you're like, I might mess this up. You always can type in 3.1, whatever the percent is, divided by 100. That'll give you the decimal form. Annually. The end value is how often does it occur. Like before we did it monthly and it'd be 12, weekly and it'd be 52. Annually just means it happens once a year. That's kind of boring. But I want this one to be flexible. And that's all I'm doing. It doesn't ask me to find the actual value in any year. I could if I wanted to, but it just asks me to set up the expression, so I'm done. So can't get much better than that. Okay. Then we got money in two different accounts. Now, there's a couple different ways we could do this. Okay, we've got one account, and again, we've got both the equations, so I'm just going to jump into that right here. But basically what the question's asking is we have two accounts, and within those two accounts, we're trying to see which one's better short-term, which one's better long-term for me. Oops, but not going to be better for me if I don't type it in correctly. And no, it's not time for you to leave. Wishful thinking, wishful thinking, wishful thinking. And 365, since I don't have the t there, I will use x. Now, I'm going to show you a couple of ways that you can do this. Okay, this is the one that we've done before and that I actually like the most. If I pull the charts up, I notice, okay, the first one I make 3,000 the first year, the second one I make 2,600. How long do I make more at the first job, okay, for account A? So I'm going to keep scrolling down until the B column, or the Y2 column, gets bigger than the first one. And I see it takes about 12 years. So the question is, which is a better investment for what time period? Explain thoroughly. Okay, so A is better for the first 11 years. So if you're only going to invest in something for like 10 years or less, count A is a better option. I'm going to end up with more money. But B is better for 12 plus years. So like if you're doing it in a retirement account, you're not going to retire for 30 years. B is the better option. But again, when it says for what time period, you've got to really explain, here's the one that's better at this time and here's why. Maybe it'll say which is the better long-term investment, the short-term investment. I don't know. It depends. But that just lets you have some flexibility to be ready for no matter which one that you get on that. Okay? All right. So as we flip over here, probably get another bell coming here because we're during the class day, but that's all right. All right. Identify transformations of the logarithmic function. So, as we're doing this, remember with my movements, inside the parentheses is left and right, outside's up and down. So, the up and down part is always the part that people seem to have an easy time with. They're like, okay, the one on the outside, down 8, okay. But what about in here? Now, your instinct would tell you negative should be left, but it's not that. Because the actual form is x minus h, the opposite of this. The opposite of negative 2 is positive 2, which means we're going right 2. So inside the parentheses, negative is right, positive is left. Outside, negative is down, positive is up. And that's it. Solving the equation. Again, before I can solve it, I got to isolate the log part. So we'll cancel those guys out. And once we've done that, so now that we've got the log isolated, how do I get rid of log 2? Wow, you're like, dang, that seems like forever ago. When we need the inverse of a log, we use that number's base. So if this had been like 5, I'd use 5 here. Okay, if this were 10, this is 10. And I do it to both sides. And remember, this is what's called exponentiating. Okay, exponentiate. Okay, base, exponent. These are turning into exponents now. Log base 2 and 2 are inverses. They go away. But this isn't 2 times 3. It's 2 to the third power. It's 2 times 2 times 2, which is 8. And then I just subtract the 3 over. Okay, but I got to do the exponentiating. If I don't, kind of tough. Okay. Another one with an exponential equation. We can kind of do the same thing. I look at the side. I'm going to rewrite this because I'd like to work with it being a little bit bigger than it is right now. There are a couple of routes you can go. If I know 3 to what power is 81, I could just make a change and have my bases be alike. But I have a feeling for a lot of you, you like doing the same thing. So here, I need to inverse log. I use the base. Now I have the base. We're going to use the inverse of the log. Okay, those things are interchangeable. So that just leaves me with the 3x plus 1 on the left. Now on the right, this gets a little more interesting. I need to be able to type this in my calculator. So to do that, I'm going to type in the log of the 81, the log of the big number, divided by the log of my base. So when I'm doing that, it was funny, I was about to do it on my own calculator. That wouldn't help you out very much now, would it? So I've got the log of 81 divided by the log of 3, which is 4. That equation just got easy all of a sudden, didn't it? Minus my 1 over, divide by 3. And again, the nice thing with these is if you're kind of looking at them sometime and you're like, holy cow, I don't remember how to do this. Okay, nice thing, section numbers on here. So if you need to go back and look at something, you can, okay, with our notes. Or just use some of the words here. Exponential equation, type it on my YouTube page, type it on my website. Stuff will pop up to help you if you're not sure. And that basically covered all the stuff we did in Unit 4, which is, again, like forever ago. Okay, Unit 5. Simplify multiplication division problems involving a rational expression. In other words, factor the crap out of these and then cancel stuff. Okay, let's do it. Anything in common, the golden rule. Somebody better say yes. Yes, there is something in common, x. So x times x is x squared, x times 2 is 2x. We're good there. Move my way down here. Factoring. Oh, the F word is back. Okay, remember, it's a diamond though. Multiply to get the numbers on the end, add to get the numbers in the middle. So what multiplies to 10 and adds up to 7? That's right, 5 and 2. What about this middle thing? There's nothing else to do and they don't have anything in common. No problem. You're like, why do you keep putting parentheses around everything too? Remember, they're bonded by the plus or minus. I'm putting the parentheses to remind me I can't cancel these x's out. I can't cancel these 2's directly out, but we'll be able to because they're identical terms. And think about that too in a minute. What happens when we divide by a fraction? You've got to flip this, and it becomes multiply. And if I can factor something, again, I've been pounding or harping on this for like months. They're both perfect squares. What can I square to get 4? 2. What can I square to get 25? 5. 1 plus and 1 minus to get me my negative 25. And now I can go on my canceling spree. I can cancel top to bottom in a fraction. I can cancel across fractions as long as one's in the numerator and one's in the denominator. Whack those guys some more. And then let's see what we've got left. Just an x up here. And a 2x plus 5 down here. Now reminder, bonded. Don't even think about it. You're done. Okay, cancel those. That'd be bad. Add rational expressions by rewriting with a common denominator as some of you start to groan. Factor what we can. Again, I'm multiplying to a negative, so I know for sure it's plus and minus. I also know the negative is going to be the bigger number because the add number ends up negative. So 4 and 3. And so then, again, my LCD is every unique set of parentheses I see, which would be both of these. So x plus 3 and x minus 4 are both in here. And remember how we used to do this. We said, oh yeah, old to new. Check off what you have. Whatever doesn't get checked off, I need up in the numerator. And if everything checks off, I really don't need anything, but I guess I can put a 1 in there. And I've done the hard part. Now I just got to remember to distribute and combine like terms. Notice I'm not losing my denominator. So 3x, 3 times negative 4 is negative 12. Plus 2 is negative 10. Nothing else factors. Bonded, 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 bonded everywhere. I'm done. Now sometimes I just got to make sure too that I don't do too much. What's the LCD? It doesn't say solve. It just says what's the LCD? So all I care about is this part right here. I still need to factor it though. And again, factoring is a skill. It just takes time and practice because you start to see patterns develop. Here, they're both perfect squares. 5 times 5 is 25. X times x is x squared. So I can get rid of that. What about these two? Now, 5's not a perfect square. Well, what can I do? Ooh. Do they have anything in common? They do. They both have an x. X times what is x squared? X times what is negative 5x? And now to get my common denominator, reminders. Okay, when we're doing these, first, I look for numbers that are hanging out on their own. And then I count, you know, if I made a list, what would they be? Well, I don't have any of those. I don't have to worry about that, so that's okay. Second, do I have any single variables that are just hanging out on their own, not connected? I do. So that's part. And then finally, I look for the different sets of parentheses that I see, and I need to use all of them. So I need an x plus 5. I need an x minus 5. But I already have an x minus 5. I don't need a second one. That's going to be my LCD. Okay, so you're starting to see, you're like, okay. A little of it's starting to come back, but whew. All right. Identify, describe, and correct student's error when trying to add the rational expressions. Here's the original problem. Okay, what's the error? Well, I noticed the LCD is right. They got that part. That's good. But wait a minute. Aren't they supposed to, when they're checking things off? Oh. Now I see what this person was doing. That was kind of silly of them. What's the error? Never built the numerator. You know, they just left it there. They're like, oh, I made the denominator the same. That's good. Yeah, no, it isn't. Not good. So then we might as well go ahead and fix this. So let's see here. X squared minus 4x plus 3x. Because I'm doing all my distributing. Plus 3 over all that good stuff. And now I just got to combine like terms and I will have the right answer. Nice, okay? But again, I got to explain where that error is coming from and kind of work it from there. So as we move up a little bit here, okay? What are the excluded values? Makes denominator equal 0. Because I can't divide by 0, it's undefined. So again, I don't care about anything that's up here in the top. I'm just looking at these guys. And I want to make sure that they do not equal 0. But I solve them like an equation otherwise. Minus the 8 over. X cannot be negative 8. We're here. I'll add the 64 over. Haven't talked about this yet. How do I get that squared off my x? What's the inverse of it, or the opposite? Square root. Okay, so we've avoided step 1 of our issue. But what does that squared mean again? How many answers are there going to be? There's going to be 2. Oh, yeah, plus or minus. So x can't be negative 8 or positive 8, and I'm good. Okay. And I go from there. And now we get to what we're currently working on. Okay, this should be the stuff that's a little bit easier. Correctly calculate the distance a minute hand of a clock traveled over a time period using the arc length formula. Okay, the arc length formula. Radius times my degree measure in radians. Determine the distance the 8.5 inch long minute hand of a clock travels between the times of 8 a.m. to 11 a.m. Okay, well, first easy part is I know my radius is 8.5 inches. Now, the degree measure, that's a little more interesting. So let's think about this. 8 a.m. to 11 a.m. How long of a time period is that? 3 hours. And every time that you have an hour when you're dealing with the minute hand, it goes all the way around. So, all the way around in a circle is 360 degrees. But my angle measure has to be in radians. Otherwise, it doesn't work right. So you're like, oh, crud. 360 in radians. How's that work again? Well, let's do a little scratch work here. Times pi over 180. Okay, reduce the numeric part. Don't include pi, especially if you do math enter enter. 360 divided by 180, if you check into it, is 2 pi. So 3 hours times 360 degrees per hour equals 6 pi. That's my angle measure. Got my radius, got my angle measure. And normally, since we're talking about distance, we don't go up to somebody and say, hi, it went 8.5 times 6 pi. Yeah, probably not. So, times 6. Pi is second in the up arrow button. If you use 3.14, that's okay. Move a little over 160 inches, quite a little distance there. All right, identify the amplitude and period. Okay, this should be the easiest one we have in the whole sheet. Amplitude's 5. Period, remember, I'm not just asking for the b value. Okay, the b value is 1/3, but that's not the period, that's just the number of cycles. Dividing by 1/3, same as multiplying by 3. Gives me 6 pi, and I'm good. Ladies and gentlemen, you have almost survived. It's tremendous. I mean, just look at all the stuff you've dealt with this semester. Shoot, that's just something to be proud of right there. Okay, accurately graph 2 cycles, not just one, of a sine or cosine function when you're given this equation. Okay, so 4 cosine of 2 theta. Well, let's see here. You're like, Harty, why are you making 2 sets of 4? Because again, we're going to do 2 cycles. We'll fix that. My a value is 4. So 4 and -4. Nope, still not time to go nowhere. So my b value is 2. So my period is 2 pi divided by 2, or just pi. So normally, there's all the lines that we're looking at. So I'd stick pi there. Okay. And when we've built in the past, again, we know we're starting at 0. It's between 0 and 1. A half is, or pi over 2. Okay. What's in between 0 and a half? Okay, would be a quarter. Now we've talked before about, well, what if I forget that? You know, how do I get that value? Remember, dividing, when you're looking for the midpoint, you're dividing by 2, which is the same as multiplying by a half. Pi times 1 is pi, 2 times 2 is 4. That's where I came up with that from. And now when I go to get all my other lines, I mean all of them through here, it's just a pattern. So it's 1/4, 2/4, which is pi over 2, 3/4, which doesn't reduce, that's why I left it there, 4/4, which is 1 or just pi. And if I want to write the rest of these down, just so, and then go and reduce them. 5/4 doesn't reduce. 6/4, they're each divisible by 2, so I'll do that. 7/4 doesn't reduce, and 8/4 is 2. So basically, here's what I've done. Here is going to be my first cycle, and then here, my 1, 2, 3, 4, 5 points, that's where my second cycle is going to end up. So now it's time to graph. Cosine starts at the max. Sine starts at 0, cosine starts at the max, unless there's a negative a value. So max, 0, min, 0, max, there's one cycle, 0, min, 0, max. One cycle, 2 cycles. Awesome. Okay, last one. Now, this is something that we have not touched upon. No, it will not be on the final. Will it be on the post? Yes. We're going to do several just to get you ready, because it's not a terrible concept. It's just not something you've seen yet. Okay? So we're going to do a little application with our graphing. So just stick with me. Okay. The height of the water in a bay varies sinusoidally, ooh, just that big word, over time. On a certain day, a high tide of 12 feet occurred at 5 a.m., a low tide of 4 feet occurred at 3 p.m. Write a model for the height of the water as a function of time. Now, that just all sounds like gibberish right now. So let's do some stuff that may be a little more sensible for us here. Okay, it's going to look just like the graphs we always do. So let's see what I know. Okay, these are going to be cosine functions. I'm just going to tell you right now. So you're not going to have to think about that. Okay, always going to be cosine. So that's a nice thing to know. Okay, on a certain day, the high tide, the max value of 12 occurred at 5 a.m. and a low tide, a min of 4 feet, you're like, wait, 4 isn't negative, just work with me, occurred at 3 p.m. It's still not time to go. Write a model for the height. Okay, you're like, well, what else am I going to need? I mean, I still need to know, okay, I still need to know the amplitude. I still need to know if there's a b value. And now this k, or sometimes we'll say it as c, are my up and down shift. So here's how we're going to play with this. When I look, I'm going to say, okay, we're going to have to go way back for a second here. When we talked about a midline before, okay, the midline is just the middle of where my min and max are. So what's right in the middle of 4 and 12? If I add them up at 16, divide by 2, it's 8. So my midline is going to be 8. So as I look at this, I go, okay, my midline's 8. Mercy, there's too many bells during these planning periods. My midline is 8, though. So if my max started here, I know it's going to go max, 0, back to my max. That's what my curve will look like. So you're like, okay, I still don't see where this is going to help me, but I'll work with you, Harty. Okay, so if my curve looks like this, how far is it from my midline to my max? 4. How far is it from my midline to my min? 4. What's my amplitude? 4. Okay. So once I know what value's in the middle of my min and max, okay, I write that down, and the distance between the two is going to be my amplitude. So I have that part ready. Next, we're going to find our b value. Now, my b value is going to be taking 2 pi divided by my period. So basically we're just doing the opposite of our normal formula. Normally we take the period, we do 2 pi over b. But if we interchange it, I can find the b value. So, you're like, but wait a minute, I don't know the period. Sure I do. 5 a.m. is where I started. Okay, I hit my bottom down here at 3. So, how long is it from 5 to 3? Because that number of hours is what I'm going to be looking for. In this case, that would be, I almost slipped up there, because as I started to look, I was only looking from here to here. My period would go from start to finish. So, I'd say, okay, from the high tide to the low tide here, it's not part of my graph, I'm just kind of labeling things for us, is 10 hours. If that same continued, that same pattern, from low back to high, would be another 10 hours. So 10 hours and 10 hours would be 20 hours. And 2 over 20 reduced is pi over 10. That would be my b value. And then finally, my 3, okay, my c value, or my k value here, is just going to be whatever my midline was, whatever's in the middle of my max and min values, which is 8. So my equation for this would be 4 cosine pi over 10 x plus 8. Now again, first look at these. do not panic. It's not showing up in the final. It's just, we're going to see if we can start making some more applications with this. We'll see several more of these again before we try to do it, you know, on any sort of a post test or anything like that. So try some of these out on the extra worksheet that you've got, and we'll chat some more tomorrow.